To make amines, we have a number of reactions available, many of which you're really familiar with, and the others will be easy for you to understand because they're going to be similar to reactions or use reactions that we've already gone over. We can form amines by reducing several different functional groups, nitriles, amides, nitro groups. We can do SN2 reactions that have nitrogen as the nucleophilic atom. Some we have to reduce afterwards, like the azide. The phthalimide, we have to hydrolyze it, but these will make a lot of sense right here. We're going to find that we can make amines from reductive amination. This uses an imine or an enamine, and you're going to see that this is relatively easy to understand. All we have to do is form the amine and then do reduction, so it makes sense. And then we have an amide or acyl azide rearrangement. This is going to be a little harder to understand, a little bit stranger, but you'll catch it. We've already seen all of these reactions. Nitriles being reduced with lithium aluminum hydride, amides being reduced with lithium aluminum hydrides, and even nitro groups being reduced with lithium aluminum hydrides. All of them make amines, primary amines. With the aromatic nitro groups, we have more reduction steps available to us depending on what we would prefer to use. Tin or tin 2 chloride and acid or hydrogenation will also take a nitro group down to an amine. Here are some examples. In the top one, you have a nitro benzene compound being reduced with hydrogenation. In the bottom one, what we have is tin 2 chloride and acid reducing the nitro group. Why was the tin 2 chloride chosen for the benzaldehyde nitro group? Because if you recall, hydrogenation will reduce a carbonyl adjacent to a benzene ring down to a methylene group. Remember that? So that's why this particular reducing agent was used. If you use lithium aluminum hydride, it would reduce this down to an alcohol. So you have to choose which one will work in a particular circumstance. When we look at SN2 reactions, you probably will look at this and say, oh yes, ammonia can do an SN2 on an alkyl halide. And it can. And a primary reaction is what would happen because the ammonia is basic. The problem is that the resulting product of this displacement, the amine, the amine, is nucleophilic also and can do an SN2 on any remaining alkyl halide. And so this becomes very messy. Let's look at an example. If I take octyl bromide and treat it with ammonia, I can get a good bit of mono substitution, but that amine then can do SN2 on any remaining octyl bromides, and we get a good bit of dioctylamine. We even will get some of the tri-substitution and even some of the quaternary ammonium salt. So it's a mess. It would be very hard to work this up and isolate anything useful. So how can we get around that? Well, instead what we do is we use sodium azide. If we look at this, this is sodium azide, and it's got a nucleophilic nitrogen on there. This is N3 with a negative charge on it, and the nitrogen on the end is nucleophilic, and it does an SN2 quite well on a primary alkyl halide. Once we form the azide, then what we can do is treat it with lithium aluminum hydride, and we get excellent reduction down to the amine. Notice DMF was used here to help accelerate the SN2 reaction. Here's an example. Here we have an alkyl halide, a primary alkyl halide being treated with sodium azide to give us the azide, alkyl azide, and then lithium aluminum hydride reducing it down to the amine. Notice here they're using ethanol, and you might question that saying, but this is SN2 and you've got a protic solvent here. Well, that's true, and the protic solvent would slow things down. It helps to solubilize this, but it would slow things down. A better solvent to choose would be DMSO or acetonitrile. But because the only reaction that can occur here is SN2, this is it will go ahead. It's just going to be slowed down a little bit by the ethanol. This is another way that we can do an SN2 to get an amine, and let's look down here at potassium phthalimide, right down here. Potassium phthalimide has a nucleophilic nitrogen. This nitrogen, this was an amide here that's been deprotonated, and you can deprotonate this amide with potassium hydroxide to get the potassium phthalimide. It's relatively acidic. This is very nucleophilic. It's the non-bonding pair that is stuck out here. There'd be two non-bonding pairs on this nitrogen. One is held in resonance with this, and then the other is stuck up out in an sp2 orbital. And because it's the groups that are on it are held back, it's very much available for an SN2 reaction. And it does a great SN2 on a primary alkyl halide. And we form this alkylated phthalimide. Once this alkylated phthalimide is formed, we can treat it with sodium hydroxide, and this cleaves quite easily. We don't have to cook it much at all. We can cleave this with sodium hydroxide and water, and we get this is called phthalic acid, and easy to remove because now we have a base and an acid, and this can be removed with sodium hydroxide to give us the amine left behind. Here's an example. This is a primary alkyl halide. We're treating it with potassium phthalimide, and then washing with sodium hydroxide to give us this amine. Here's an example of using sodium azide. Sodium azide on this primary alkyl halide, treating it with lithium aluminum hydride afterwards gives us this amine. Reductive amination. You can form primary, secondary, or tertiary amines, and the carbon on which the amine is can be primary, secondary, or tertiary, because, well, not tertiary, primary or secondary, because of the way in which this is made. So you don't have to worry about steric hindrance. You can do this on a secondary carbon. You can have substituents on your nitrogen, so it's really a very useful reaction. You start with an aldehyde or a ketone, which you can get from an alcohol or a lot of other functional groups, and you treat it with ammonia or an amine. What happens, you've seen this already, that you form an imine or an enamine. Once you form this, you can reduce this. Now, I'm showing you sodium cyanoborohydride. The book gives you sodium borohydride. You can use either as a reducing agent here. It doesn't matter. The sodium cyanoborohydride is a little bit gentler and will not reduce any carbonyls that might happen to form by reversal of the imine or enamine. The idea is you need a reducing agent. So either pick sodium cyanoborohydride or sodium borohydride. So what we have here is a ketone. We're going to treat it with ammonia. That forms an imine right here. So we would get a nitrogen here with a hydrogen off of it. We can reduce it then, and what do we get? An amine on a secondary carbon. We can't get this by doing SN2 because SN2 would be in competition with E2. And so this is a very useful reaction for secondary carbons, not secondary amines, realize. I'm talking about the carbon. Here's another example. Here we would form an enamine because this is a secondary amine. So this nitrogen would end up here with the 2 methyls off of it. You would treat it with sodium cyanoborohydride, and it gives you a tertiary amine here. Here's another example, treating an aldehyde with a primary amine, then treating with sodium cyanoborohydride. Look what we get. We end up getting the secondary amine. Here, these become an alkyl group on the nitrogen, and then we have that alkyl group already there, right here. If I treat acetone with pyrrolidine, I make the enamine. Sodium cyanoborohydride reduces it down to this tertiary amine then. The last way to form amines that we're going to look at are 2 reactions. You've never seen anything like these before, and they're going to seem a little unusual, but they're similar to each other, so you might be able to understand them through their similarity. In both of them, you take an acid functional group, an acid derivative, and you rearrange it to then give you an amine. Let's look at this first type. You take an amide and you treat it with bromine and sodium hydroxide, and you end up with an amine. This R group right here swings over onto the nitrogen, and then you lose this carbonyl, and you end up getting a primary amine. How does this occur? Well, under equilibrium conditions, the sodium hydroxide will deprotonate this nitrogen, which then is brominated. Equilibrium conditions again with the sodium hydroxide will deprotonate this nitrogen, and that causes rearrangement. The R group swings over here, and you form something called an isocyanate, which then in water adds water. It hydrates to something called a carbamic acid, which decarboxylates and then gives you this primary amine. Do you need to know the mechanism? No. What you need to remember is that under these conditions, you have this R group swing onto this nitrogen, and you lose the carbonyl. You have a similar reaction occurring with an acyl azide. If we take a carboxylic acid and treat it with thionyl chloride, we end up getting an acid halide, which when treated with sodium azide gives what is called an acyl azide. If I heat this, it rearranges to an isocyanate, just like in the previous reaction. If you treat the isocyanate with water, it then forms the carbamic acid, which loses carbon dioxide to form this primary amine. So what we see in both of these is an isocyanate intermediate, and in both of them what happens is the R group swings over onto a nitrogen to form the primary amine. So do you need to know the mechanism of either of these? No, just remember you lose a carbon from the carbon chain, and the R group that was on the acid derivative ends up being on the amine, and it's a primary amine. Here's some examples. Here is an amide, treating it with bromine and sodium hydroxide in water. What do we get? This amine. This nitrogen ends up being right here where it was attached. Here's a carboxylic acid. Treat it with thionyl chloride, sodium azide, and heat. And what happens? You get the isocyanate forms here, and then it rearranges to give you an amine here.